The Atlantic between Florida, Puerto Rico, and Bermuda looks like any other stretch of open ocean. Blue-green water, wind, nothing that suggests a place where aircraft and ships have disappeared without leaving a clear trace. But on December 5th, 1945, five United States Navy aircraft took off from Fort Lauderdale on a routine training flight. 14 men were aboard. 2 hours later, their flight leader reported that the compasses were no longer working and that he could not determine their position. The radio transmissions became increasingly confused. Then the aircraft disappeared. A rescue plane was sent after them. It disappeared too. 27 men and 6 aircraft were suddenly gone, and no confirmed wreckage from Flight 19 was ever recovered. The strange part is that there was no major storm recorded in the area when the flight vanished, and the story that would eventually become the Bermuda Triangle did not even begin with that disappearance. The name came nearly 2 decades later. Beneath the surface, however, the ocean is far less ordinary than it looks. A powerful current moves through this part of the Atlantic at roughly 9 kilometers per hour, about 5.6 miles per hour, carrying an enormous volume of water that can scatter debris far from where a vessel actually sank. Farther north, beneath hundreds of meters of water, enormous deposits of frozen methane lie within the seafloor. Some occur at depths of roughly 300 to 1,200 meters, around 1,000 to 4,000 feet, and when these deposits destabilize, the water above them can become violently disturbed as gas escapes upward. Farther south, the seafloor drops to nearly 8,400 meters, about 27,500 feet at the deepest point in the Atlantic. Down there, the ocean is completely dark, under immense pressure, and still being shaped by geological forces that have been operating for millions of years. None of this requires anything supernatural. The ocean itself is complicated enough. Currents can move what sinks, gas can alter what happens beneath the surface, and geology can create landscapes that remain almost completely invisible from above. The Bermuda Triangle became a legend because people looked at what disappeared. The stranger's story may be what was already happening beneath it. Tonight, we're going beneath the surface of the Bermuda Triangle to follow the currents, gases, and geological structures that make this ordinary looking stretch of Atlantic far more complicated than it appears. A map of the western North Atlantic gives the Bermuda Triangle an appearance of certainty that the sea itself never possessed. Draw a line from Miami to Bermuda, another toward San Juan in Puerto Rico, and close the shape, and a familiar triangle appears. Those boundaries belong to the story people tell about the region. They are not recognized limits on official navigation charts, and no government designates the area as a special maritime hazard. Within that loose shape, the seafloor changes more dramatically than the simple geometry suggests. Near the Bahamas, broad shoals bring the water to depths of about 20 feet, with the bottom close enough to influence everything above it. Farther offshore, the floor descends through shelves and slopes toward the deep Atlantic. At the southern margin, the Puerto Rico Trench reaches 27,493 feet at the Milwaukee Deep, more than 5 miles below the surface. Across one region, the vertical difference approaches the height of a major mountain range turned upside down. The surface geography is just as varied. The Gulf Stream threads through the western portion, carrying warm water northward. The Sargasso Sea occupies the center of the great North Atlantic circulation, enclosed by currents instead of coastlines. Along the northern side, the Blake Plateau forms a broad underwater platform before the continental margin falls toward deeper water. The Puerto Rico Trench marks the southern boundary, with a narrow depression carved by the meeting of tectonic plates. This makes the triangle less like a single place and more like a crossing point between several oceanic worlds. A vessel can pass from shallow limestone platforms into deeper open water within a relatively short journey. Far below, the character of the floor changes again from continental rock and sediment to abyssal terrain shaped by currents, landslides, and the slow movement of Earth's crust. Human traffic passes through all of these environments. Ships carrying cargo between the United States East Coast and the Caribbean cross the region throughout the year. Cruise vessels leave Miami and travel toward islands scattered across the Caribbean. Aircraft cross overhead along routes connecting North America with the Caribbean and beyond. The same waters that became associated with legendary disappearances are also part of an ordinary transportation network used by thousands of people. The geography becomes more interesting when viewed vertically. Imagine the region as a layered column rather than a triangle on paper. At the top is moving seawater with currents carrying heat and floating material across enormous distances. Below that lies the continental shelf, followed by the steeper continental slope. Deeper still are sedimentary plains and the deposits accumulated through millions of years of ocean history. At the southern edge, the Puerto Rico Trench cuts far below the surrounding floor. Each layer has its own temperature, pressure, chemistry, organisms, and geological history. Together, they form a three-dimensional landscape extending from sunlit water to the deepest reaches of the Atlantic. The familiar triangle is therefore only the outline seen from above. The real geography begins when the surface is treated as the first layer of a much larger world. At the surface, that layered world is already in motion. Water enters, leaves, circulates, sinks, and rises through pathways that ignore the imagined borders of the triangle. The geography is therefore alive, changing from moment to moment, while the deeper architecture remains rooted in geology. The Gulf Stream can be felt before it can be seen. A ship crossing the western Atlantic may pass through water several degrees warmer than the surrounding sea, entering a moving body whose boundaries are defined by temperature, speed, and density. It begins in the Gulf of Mexico, gathers strength through the Florida Strait between Florida and Cuba, then bends northeastward past Bermuda before continuing toward Western Europe. At the Florida Strait, surface water can reach speeds of 5.6 miles per hour. The current stretches roughly 50 miles across and reaches depths approaching 2,600 feet. During summer, its surface temperature can approach 80 degrees Fahrenheit, creating a broad thermal signature that satellites can distinguish from the cooler water around it. The boundary is not a painted line on the ocean, it is a shifting meeting place between water masses with different histories and different amounts of stored heat. The scale becomes easier to sense through its volume. Around 30 million cubic meters of water, which is about 1.1 billion cubic feet, can pass through the Florida Strait every second. The Amazon River carries roughly 200,000 cubic meters per second, about 7 million cubic feet. The Gulf Stream therefore transports around 150 times as much water as the world's largest river, a moving column of seawater large enough to reshape the journey of anything caught within it. A piece of wreckage entering this flow does not remain where the vessel disappeared. At 5.6 miles per hour, a floating fragment can travel more than 33 miles in 6 hours, while a full day allows the current to carry material more than 130 miles. Wind, waves, sinking speed, and the different shapes of individual fragments spread the field still farther. A search conducted hours after a loss may therefore be looking at an empty coordinate, while the evidence is already scattered elsewhere. The current also changes the atmosphere above its surface. Warm water releases heat and moisture into passing air, especially where colder air masses cross the stream. Along these boundaries, squalls can develop rapidly, strengthen, and move away within a short period. A vessel may encounter rough weather that has disappeared from the same location by the time another aircraft or ship arrives. The ocean continues carrying heat even after the clouds have moved beyond the horizon. Bermuda itself owes part of its existence to this circulation. Warm water carried north from the tropics helps maintain coral communities around the island at a latitude where such reefs would otherwise struggle to persist. Those reefs contribute to the limestone platform that forms Bermuda's familiar surface, built upon a volcanic seamount whose eruptions ended millions of years ago. The current, therefore, supports a living structure that rises from geology far older than human navigation. Farther across the Atlantic, the same circulation transports tropical heat toward Europe. The energy carried northward influences regional climate, making parts of Western Europe considerably milder than their latitude alone would suggest. Inside the Bermuda Triangle, the Gulf Stream is therefore more than a current crossing a map. It is a moving boundary, a transporter of heat, and a force capable of carrying physical evidence far from its starting point, all while continuing along its immense Atlantic pathway. At the western edge of the triangle, the ocean floor begins as a broad platform rather than a plunge into darkness. The Bahamian Shelf spreads beneath the islands in pale bands of sand, limestone, and coral debris. In places, the water above it is only about 6 meters deep, which is about 20 feet, shallow enough for sunlight to reach the bottom and for the seafloor to remain visible from above under favorable conditions. This shelf was shaped through repeated changes in sea level. During ice ages, enormous quantities of water became locked in continental ice, lowering the oceans and exposing areas that now rest underwater. Rivers once crossed these exposed plains, carrying sediment toward the outer margin. When the climate warmed and the ice melted, seawater returned, covering those landscapes and preserving portions of their old drainage patterns below the present surface. The Bahamas are especially striking because much of their foundation consists of carbonate rock produced by marine life. Tiny organisms extract minerals from seawater, build shells and skeletons, and leave their remains behind when they die. Across immense spans of time, those fragments accumulate and become limestone. Caves, channels, banks, and terraces develop within the rock as seawater moves through it, giving the shelf a structure far more intricate than a smooth layer of sand. Around Bermuda, coral adds another living dimension to the platform. The reefs grow on the summit of an extinct volcanic seamount, where warm tropical water carried by the Gulf Stream allows coral communities to persist at roughly 32 degrees north latitude. Their limestone framework gradually builds upward and outward as generations replace one another. The island visible today is therefore connected to two very different histories: volcanic activity deep in geological time and biological construction continuing much later. Each layer records a different chapter with no sharp boundary between geology and life, sediment, reef, and volcanic stone sharing one changing landscape. For early mariners, these shallow structures could become difficult to read. Coral heads and limestone ridges may rise close to the surface while remaining difficult to distinguish from surrounding water, especially when waves, glare, darkness, or poor visibility obscure the bottom. A vessel traveling at speed has little time to react after a submerged obstacle appears. Wrecks accumulated around the reefs over centuries, leaving a physical record of navigation meeting an intricate seafloor. Farther offshore, the shelf carries another memory of lower sea levels. Submarine canyons cut across portions of its outer margin, following routes established when rivers reached much farther toward the sea. Later, sediment flowed through these channels in dense underwater currents, carving and deepening them. Their walls can interrupt otherwise regular terrain, producing sudden changes in depth across a relatively short distance. These buried landscapes matter to modern oceanographers as well. Sonar signals returning from uneven limestone, loose sediment, and canyon walls can produce complicated patterns requiring careful interpretation before a detailed map emerges. The shelf therefore contains both a geological archive and a navigational landscape assembled through changes that occurred long before modern vessels began crossing the Atlantic. Eventually, the broad platform narrows toward its outer boundary. Sandbanks and shallow limestone give way to a margin where accumulated sediment begins descending toward deeper water, and the gentle architecture of the shelf starts to tilt into the open Atlantic. At the shelf's outer margin, the seafloor changes its angle, and the broad platform begins to descend toward the deep Atlantic. This continental slope can drop roughly 1,000 feet over a horizontal mile, creating a terrain whose scale is difficult to sense from the surface. Sediment and fractured rock form a long boundary between continental crust and the deeper ocean basin. The slope is not a single smooth wall. Ridges, gullies, terraces, and channels interrupt its face, shaped by gravity and by the movement of material from shallower water. Fine particles settle gradually, while heavier sediment can gather until an earthquake, storm, or other disturbance sends it downslope. The material then moves as a dense flow, carrying sand, mud, shells, and fragments across terrain that may have taken millions of years to form. These sediment flows can reshape the slope with surprising reach. A submarine landslide may begin as a small failure and gather speed as it travels, transforming into a broad avalanche of seafloor material. Documented underwater slides have reached speeds approaching 60 miles per hour. As they race downward, they can scour channels into the slope and spread thick deposits across the floor below. The deepening landscape eventually gives way to the abyssal plain, where the terrain becomes more expansive and much less varied. Across large portions of the triangle, this floor lies between 15,000 and 20,000 feet below the surface. Pressure there reaches roughly 7,000 pounds per square inch, hundreds of times greater than the pressure at sea level. The temperature remains only a little above freezing, while sunlight has long since disappeared from the water column. For a vessel lost near the shelf edge, gravity determines the final direction. A wreck can slide, roll, or settle as it follows the contours of the slope, eventually reaching deeper ground. Once it comes to rest on the abyssal plain, its location becomes part of a landscape that is difficult to survey from above. During the middle of the 20th century, searching thousands of feet below the surface was limited by sonar range, navigation accuracy, and the inability to place instruments directly on the seabed. Even modern surveys leave enormous stretches of deep water examined only intermittently. A search may identify the general terrain while missing smaller wreckage, sediment-covered objects, or features concealed within uneven ground. The seabed can also change after a loss, as fresh sediment spreads across older layers and gradually alters the appearance of the site. A wreck may become part of that new layer, its outline softened as particles settle across metal, timber, and cargo. The slope carries another kind of history as well. Every layer deposited there records material arriving from shallower environments, while every channel records moments when gravity overcame the stability of the accumulated sediment. The boundary between shelf and deep ocean is therefore continually being redrawn, grain by grain and slide by slide. Far below the familiar surface routes, the continental margin has become a moving archive. Its upper layers preserve traces of rivers, reefs, storms, and biological debris, while deeper deposits record older changes in sea level and climate. The descent has crossed the threshold into a realm where gravity, pressure, and sediment movement shape the landscape with forces that operate beyond ordinary human scale. On the northern margin of the region, the Blake Plateau spreads beneath the Atlantic as a broad underwater terrace. Its surface lies roughly 1,000 to 4,000 feet below the sea, where pressure and temperature create conditions unlike those found near the waves. Sediment accumulates across this plateau, carrying the remains of marine organisms downward and preserving organic carbon within layers that have been compressed for immense spans of time. Among those sediments are methane hydrates, crystalline solids formed when methane molecules become enclosed within cages of water molecules under sufficient pressure and low enough temperature. They resemble ice in appearance, although they behave very differently. A fragment brought into warmer, lower pressure conditions can break apart, releasing methane gas as the crystal structure collapses. The unusual part is the amount of gas stored inside this frozen form. 1 cubic foot of methane hydrate can release roughly 160 cubic feet of methane gas under surface conditions. The solid, therefore, acts like a compact container, holding a much larger volume of gas than its physical size suggests. Across the global ocean, methane hydrate deposits are estimated to contain thousands of gigatons of carbon, although estimates vary because much of the reservoir remains difficult to measure directly. The Blake Plateau became an important location for studying these deposits through ocean drilling. Scientists recovered sediment cores and examined the layers for evidence of hydrate formation, methane movement, and changes in the seafloor environment. The samples showed that methane had migrated through the sediment and accumulated within the pressure and temperature zone where hydrate can remain stable. That stability depends on a narrow set of conditions. Deeper sediment generally experiences greater pressure, while temperature tends to rise with increasing depth. Within the right combination, methane remains trapped in solid hydrate. Shift those conditions far enough and the structure becomes unstable. Warming sediment or reducing pressure can move the boundary of stability, allowing methane to return to its gaseous form. The history of methane hydrate release elsewhere offers a glimpse of what such changes can leave behind. On the floor of the Barents Sea near Norway, researchers have identified fields of craters associated with past methane release. Some are roughly half a mile across and about 150 feet deep. Their shapes record episodes when gas escaped from sediments with enough force to disturb the seabed itself. The Blake Plateau has its own geological history, yet its surface has not been examined everywhere at the resolution needed to identify comparable features. Surveys can reveal the broad structure of the plateau, while smaller scars remain difficult to distinguish among sediment layers and natural seafloor irregularities. There is also an important distinction between a stable deposit and an active eruption. The presence of methane hydrate does not mean a catastrophic release is occurring. Large-scale destabilization in this region has not been established as a recurring modern process, while smaller methane releases are known from many continental margins. Much of the hydrate remains locked within the sediment, responding to the pressure and temperature conditions around it. Deep below the water column, the methane therefore exists in an unusual state, neither freely circulating gas nor ordinary mineral. It is carbon stored within a crystal framework, preserved by the physical conditions of the seafloor. Its existence reveals how closely geology, chemistry, and ocean history can become intertwined in a single layer of sediment. A ship remains on the surface because the water around its hull can provide enough upward force to balance its weight. Ordinary seawater has a density of roughly 1,025 kilograms per cubic meter, which is about 64 pounds per cubic foot. The hull, cargo, machinery, and enclosed air together produce an average density lower than the surrounding water, allowing the vessel to remain supported. Methane introduces an unusual possibility when it escapes from seafloor sediments in large quantities. As gas rises, bubbles become mixed throughout the surrounding water, creating a plume in which water and methane occupy the same space. Because gas is far less dense than seawater, the mixture becomes lighter. The greater the concentration of bubbles, the greater the reduction in density. Under sufficiently extreme conditions, laboratory experiments and fluid models show that a gas-rich water column can lose much of its normal buoyant capacity. A vessel entering such a region could experience a sudden reduction in the upward force supporting its hull. The effect would occur around the ship rather than inside it, leaving the vessel structurally intact while changing the physical properties of the surrounding water. The transition would be difficult to recognize from the deck. Methane itself is colorless and has no odor in its pure form. Bubbles could rise through the water, while the surface remained comparatively ordinary, especially if the release occurred below the immediate reach of waves and wind. A crew would have little visual information about the density of the water beneath the hull. A large release could therefore produce an unusual sequence. As buoyancy decreases, the vessel would settle lower into the water. If the gas concentration became great enough to reduce support dramatically, the hull could begin descending. Once movement downward started, the vessel's mass and momentum would make recovery increasingly difficult. Deeper water would gradually restore greater density around the hull, although the vessel could already be moving too rapidly for that change to stop its descent. The scale of such an event matters. A substantial gas release from a hydrate-bearing sediment layer would involve enormous volumes of methane moving upward through the water column. Much of the gas would eventually reach shallower water and the atmosphere, where currents and turbulence would spread it across a wider area. The seafloor could also be disturbed by sediment movement accompanying the release. Evidence from other continental margins shows that methane can escape naturally through seeps and larger geological disturbances. Craters on the barren sea floor preserve traces of past gas release, demonstrating that sedimentary gas can alter the shape of the seabed. Those features establish the physical possibility of powerful methane release, although they do not demonstrate that such an event has caused a ship to disappear in the Bermuda Triangle. That distinction matters because the proposed sinking mechanism remains a hypothesis rather than an established explanation for historical losses. No confirmed Bermuda Triangle wreck has been shown to have vanished through a methane hydrate eruption. The deposits are real, the chemistry is real, and gas-saturated water can reduce buoyancy under appropriate conditions. Connecting those facts to a particular disappearance requires evidence from the seafloor, and that evidence has not been recovered. What remains fascinating is the physical pathway itself. Carbon stored in sediment can become methane. Methane can become hydrate. Hydrate can release gas, and gas can alter the density of seawater. A change that begins within buried sediment can therefore influence the water column hundreds or thousands of feet above it, linking the geology of the seafloor with the behavior of everything moving across the surface. Aviation depends on a narrow balance between fuel and air, and older piston engines were especially sensitive to changes in that balance. Their carburetors and fuel systems were designed for ordinary atmospheric conditions, where oxygen made up roughly one-fifth of the air. A large methane release could alter that mixture locally by adding another combustible gas to the atmosphere. Methane rising from the sea would not form a visible plume like smoke. The gas has no color, and pure methane has no odor. Above a major release, however, the air could become enriched with methane as bubbles reached the surface and escaped into the atmosphere. Wind would spread the gas, while turbulence would mix it with surrounding air, producing concentrations that changed from place to place. For an aircraft flying through such a region, the consequences would depend on concentration, engine design, altitude, and duration of exposure. Methane itself does not displace oxygen simply because it is present, and a modest concentration would not automatically stop an engine. At higher concentrations, however, methane can alter combustion and create an ignitable fuel-rich mixture. A spark from an electrical system or engine component could then ignite the gas and produce a brief fireball. The danger would be especially difficult to recognize over open water. There would be no mountain, runway, or nearby road to offer an alternative landing site. An engine losing power at low altitude leaves only a short interval for a pilot to establish a glide and prepare for water impact. Once an aircraft strikes the ocean at high speed, its structure can break apart into many fragments, while waves and currents disperse the pieces. The disappearance of the Martin Mariner during the Flight 19 search has sometimes been connected with this mechanism. On December 5, 1945, the large flying boat carrying 13 crew members departed to assist the search. It vanished without a confirmed distress transmission. A nearby ship reported seeing a fireball around the time of its disappearance, and records document concerns about fuel leaks affecting this aircraft type. Those details create a sequence that can be imagined within known physics. A fuel leak could produce an ignition source, while a methane-rich atmosphere could provide additional combustible material. An explosion would account for the sudden loss of communication and the absence of a conventional emergency transmission. Scattered wreckage could then become difficult to locate in moving ocean water. Still, the methane explanation remains unproven. There is no recovered wreckage demonstrating that the Mariner entered a methane cloud, and no measurement recorded the atmospheric composition at the location and moment of its disappearance. The reported fireball has other possible interpretations, including an aircraft fuel explosion unrelated to methane. The physical mechanism is plausible under specific conditions, yet plausibility alone cannot establish what happened on that December afternoon. What the seafloor contributes to the story is a connection between environments that seem completely separate. Organic carbon, buried in marine sediment, can produce methane over geological time. Methane can become concentrated within hydrate deposits, then return to gas under changing conditions. Gas released into seawater can migrate upward, and some of it can reach the atmosphere. From there, chemistry can influence combustion inside an aircraft engine or around its structure. The chain begins in sediment and reaches into the sky, joining two parts of the ocean world that appear distant when viewed from the surface. Flight 19 began as an ordinary training exercise on December 5, 1945, with 5 torpedo bombers and 14 men leaving the Florida coast. Their assignment was familiar, a navigation route over open water followed by a return to base. During the flight, the crew became uncertain about their position. Dead reckoning errors accumulated as minutes passed, while radio communication with the ground became increasingly difficult. The weather offered few reliable landmarks, and daylight was fading over an ocean where horizon and water could blend into one broad field. Navigation at sea depends on small corrections made before small errors become large ones. A heading that is slightly wrong can carry an aircraft many miles from its intended route after enough time. For Flight 19, roughly 90 minutes of accumulated uncertainty placed the formation somewhere other than where the crews believed themselves to be. Compass readings became a source of disagreement, radio contact deteriorated, and the changing light removed another reference point. With fuel running low, the margin for another correction narrowed until only minutes remained. The final location of the aircraft remains uncertain. Search vessels and aircraft covered enormous areas, yet no confirmed wreckage from the 5 bombers was recovered. The ocean offered little surface evidence to guide the search, while waves and currents could separate small fragments from their original position. A disappearance can become difficult to reconstruct even when every event involved ordinary physics. The loss of the United States Navy cargo ship Cyclops followed a different path. In March 1918, the vessel carried more than 300 men and a heavy cargo of manganese ore. The ship was about 165 meters long, which is about 542 feet, and its loaded condition placed unusual demands on stability. Reports indicate that the cargo exceeded the vessel's rated capacity, while one of its engines was unavailable. Dense cargo has consequences that extend beyond simple weight. When a ship carries heavy material high within its holds, its center of gravity can rise. In rough seas, shifting cargo can alter that balance further. A deeply loaded vessel, already operating with a reduced stability margin, can respond differently to large Atlantic swells. Once a ship heels beyond the point from which its buoyancy can restore it, recovery may become impossible. The final movement can be rapid, leaving little opportunity for a distress transmission. The most likely loss area lies over water several thousand meters deep, with some estimates placing the seafloor around 4,600 meters, which is about 15,000 feet, to 5,500 meters, that is nearly 18,000 feet. At such depths, even a wreck known to exist would be difficult to locate, and a vessel lost without a confirmed position becomes a different kind of archaeological problem. These stories remain important because they show how ordinary physical conditions can produce extraordinary uncertainty. Flight 19 demonstrates how navigation, weather, radio communication, darkness, and limited fuel can converge. Cyclops shows how loading, stability, machinery, and waves can combine within a single vessel. Neither case requires an unknown force. The deeper story begins with that ordinary complexity. The surface can conceal the sequence that produced a disappearance, while the seafloor preserves only fragments of what followed. Far below those remembered losses lies a different scale of ocean geography, where depth itself becomes part of the evidence. At the southern edge of the triangle, the seafloor gathers into a different shape. The Puerto Rico Trench stretches for roughly 800 miles along the northern margin of Puerto Rico and the Virgin Islands, forming a long depression where the ocean crust bends downward. Its length gives it a presence across the map, yet its defining feature is vertical. At the Milwaukee Deep, the bottom reaches about 8,380 meters, which is about 27,400 feet, making it the deepest known point in the Atlantic Ocean. The numbers become easier to picture when another landmark is brought into the same frame. Mount Everest rises about 8,849 meters, which is about 29,032 feet above sea level. If that mountain could be lowered into the Milwaukee Deep, its summit would remain underwater. More than 450 meters, which is about 1,476 feet, of water would still cover the highest point. A landscape that dominates the roof of the world would disappear entirely within this Atlantic depression. The trench itself has a form unlike the broad floor surrounding it. Its walls descend sharply through fractured terrain, with ledges, ridges, and slopes shaped by the immense forces acting where one tectonic plate moves beneath another. The ocean floor here is part of a subduction zone, where the North American plate is driven beneath the Caribbean plate. Rock is carried downward as the plates converge, while earthquakes release strain accumulated along the boundary. Far below the surface, pressure becomes one of the defining conditions. At the deepest point, the weight of the overlying seawater produces pressure hundreds of times greater than that at the surface. Every opening, seam, and material within a research vehicle must withstand forces pressing inward from all directions. Light from above has vanished long before the descent reaches its final stage, leaving instruments and artificial illumination to reveal the terrain one small region at a time. Human contact with this depth has been extraordinarily limited. The Milwaukee Deep has been visited fewer times than the number of human lunar landings. In December 2018, the Five Deeps expedition reached the bottom using a crude deep ocean submersible supported by the research vessel Pressure Drop. Multi-beam sonar mapped portions of the trench with a level of detail that earlier surveys could not provide, revealing variations in the walls and floor that had remained difficult to resolve. The expedition also demonstrated how much of the Atlantic's deepest geography remains dependent on remote sensing. A vessel can pass above terrain that has never been observed directly, while sonar gathers echoes from structures several miles below, across contours no diver could reach. Those echoes become measurements, contours, and digital maps, transforming an inaccessible landscape into something scientists can study from the surface. The trench lies within the United States' exclusive economic zone, yet its immense depth and difficult conditions have limited systematic exploration. Large portions of its walls remain known only in broad outline. Even in an ocean crossed by ships and aircraft for centuries, the deepest ground has retained a remarkable degree of uncertainty, preserved beneath thousands of feet of water and shaped by the slow movement of Earth's crust. A trench of this scale is easy to imagine as a wound left by some distant catastrophe, a mark impressed upon the seafloor during a single dramatic moment. The Puerto Rico Trench emerged through a different kind of story. Its shape reflects a process that never truly pauses. Every day, every year, the forces responsible continue their work beneath the Atlantic. The North American tectonic plate moves toward the Caribbean plate and descends beneath it at an angle. The pace is modest, roughly 2 centimeters per year, which is about 0.8 inches per year. Measured against a human lifetime, that motion seems almost motionless. Measured across millions of years, it becomes one of the most powerful landscape building mechanisms on Earth. The trench marks the place where the North American plate bends downward and begins its journey into the mantle below. This type of boundary is known as a subduction zone. Oceanic crust, made denser through age and cooling, is gradually drawn downward by gravity. As the plate sinks deeper, pressure and temperature increase. Minerals within the descending rock begin to change. Water and other volatile compounds trapped inside the crust are released into the surrounding mantle. Those substances lower the melting point of nearby rock, encouraging the formation of magma that rises toward the surface above. Far from the trench itself, islands emerge as expressions of the same mechanism. Martinique, Guadeloupe, and Montserrat belong to a chain shaped by volcanism linked to the subduction process. Their mountains, lava deposits, and eruption histories are connected to movements occurring far below the ocean floor. The islands and the trench appear separate on a map, yet both are products of a single tectonic system operating across a broad region. Movement along the plate boundary does not occur smoothly. Friction resists motion where the plates press together. Segments of the fault can remain locked for long periods while stress accumulates. Rock bends under strain, storing energy much as a branch bends before it snaps. Eventually, the stress exceeds the strength of the fault. The plates shift. Energy radiates outward through the crust as seismic waves. What people experience at the surface is an earthquake, though its origins may lie kilometers below, that is nearly miles below, within the plate boundary itself. One such release occurred on January 9th, 1918. A magnitude 7.1 earthquake struck near Puerto Rico. The movement disturbed the seafloor and displaced ocean water, generating a tsunami. Waves reached heights of approximately 6 meters, which is about 20 feet, along parts of the northwestern coast. Around 116 people lost their lives. The event demonstrated that the trench is not merely a geographic feature, it is an active tectonic boundary capable of reshaping coastlines within minutes. Smaller earthquakes occur far more frequently. Clusters of tremors, often called seismic swarms, appear throughout the trench region as stress shifts from one section of the fault system to another. Each event provides a glimpse into the ongoing adjustment of the crust. Geological modeling and seismic studies indicate that parts of the plate boundary possess the capacity to generate earthquakes exceeding magnitude 8. A rupture of that scale could displace an enormous volume of seawater and produce a major tsunami. Hazard assessments, prepared by the National Oceanic and Atmospheric Administration, recognize this possibility. Deep below the Atlantic, the tectonic engine that carved the trench continues its work, shaping both the ocean floor and the islands above through motions that remain active today. Gravity is something we usually notice through falling objects, ocean tides, and the weight of our own bodies. Yet, across the Puerto Rico Trench, gravity becomes a way of sensing structures that cannot be seen directly. Instruments detect a small departure from the gravitational field expected for that region, and the pattern points towards something unusual within the crust and upper mantle. A gravity anomaly is a difference between measured gravity and the value predicted from a reference model. Earth is made from materials of different densities, arranged in layers and irregular masses. Dense rock pulls a little more strongly. Less dense material produces a weaker gravitational signal. Geophysicists measure these variations in milligauss, a specialized unit small enough to reveal changes that would be imperceptible in ordinary life. The Puerto Rico Trench carries one of the strongest negative gravity anomalies known on Earth, measured at about minus 380 milligauss. The important point is not that gravity has vanished at the trench floor. The measurement reflects a gravitational field substantially lower than the chosen reference field. Something in the underlying structure produces a mass distribution that does not fit a simple picture of the surrounding crust and mantle. A United States Geological Survey report describes the trench as being associated with the most negative gravity anomaly on Earth, whose origin was, in the report's words, presently unknown. The same document connected the measurement with what it called a dynamic disequilibrium within Earth. That phrase carries unusual weight in a scientific setting because it acknowledges a mismatch between observation and complete explanation. The broad tectonic setting provides part of the picture. The plate boundary around Puerto Rico is undergoing complex motion, with the North American plate moving beneath and alongside the Caribbean plate. The descending plate bends the seafloor, while the surrounding mantle responds to the forces imposed upon it. Those movements can create changes in density, elevation, and crustal structure, all of which influence the gravitational field. Several models have been proposed to explain the trench's unusual combination of depth, gravity, and deformation. One published interpretation suggests that a change in the angle of the descending slab may have caused rapid vertical movements in the region millions of years ago. Other possibilities involve shearing within the descending plate, or even a tear in the slab. These ideas can reproduce portions of the evidence, yet the complete structure remains difficult to resolve. Part of the difficulty comes from geography. The feature lies under thousands of meters of seawater, where direct sampling is sparse and detailed measurements are expensive. Gravity alone cannot reveal exactly how rock is arranged at depth. A low reading could result from several different combinations of density and geometry, so researchers compare gravity with seismic observations, seafloor mapping, and geological evidence. That leaves the trench with an unusual scientific character. The anomaly also resists the comforting simplicity of a single measurement having a single cause. It is a fingerprint of structure, carrying information about forces and materials far below the seafloor, even while leaving important details unresolved. Its deepest mystery is measurable, repeatable, and written into the data itself. The number is not a legend created around a disappearance. It is a physical signal recorded by instruments, pointing into the earth toward a structure whose full explanation remains unfinished. The walls of the Puerto Rico Trench carry a record written in broken layers of rock. Their surfaces are fractured and folded, shaped through millions of years as tectonic forces compressed, lifted, tilted, and displaced pieces of oceanic crust. Rock can stand at angles, while sediment deposited across older surfaces becomes part of the same complicated structure. This geometry reflects the meeting of two tectonic plates. Along the boundary, the North American plate moves beneath the Caribbean plate, creating compression and deformation through the crust. Faults cut across the trench walls at different angles, and layers of sediment mingle with volcanic material carried from the island arc. Each layer records a different interval of geological history, while the fractures reveal where that history was disturbed. Gravity also works on these steep surfaces. Sediment settles into pockets and ledges, gradually building unstable accumulations. An earthquake can shake those deposits loose. Changes in water within the sediment can reduce its strength. Continued accumulation can also push a slope beyond the angle it can maintain, allowing a mass to detach and begin moving downslope. Once released, the sediment can transform into a dense current that travels along the ocean floor. These turbidity currents carry enormous quantities of mud, sand, and broken material, spreading them across distances that can reach hundreds of kilometers, which is about hundreds of miles. Their movement can continue far beyond the original slide, laying down sediment over terrain that may have taken thousands of years to form. One of the clearest demonstrations came in 1929, when an earthquake beneath the Grand Banks off Newfoundland triggered a submarine landslide. The resulting turbidity current raced across the seafloor at speeds approaching 97 kilometers per hour, which is about 60 miles per hour. Along its path, the current snapped transatlantic telegraph cables one after another. The sequence of breaks gave scientists a rare way to reconstruct the movement of material through the deep ocean after the event had already passed. At depth, the weight of overlying water does little to stop this process. Sediment remains subject to gravity, while earthquakes can provide the brief disturbance needed to overcome friction between grains. Once motion begins, the boundary between stable ground and flowing material can shift across the seafloor, carrying its own momentum into deeper regions. The same physical process operates wherever steep submarine slopes become unstable, including the complicated margins around deep Atlantic trenches. A slide can bury equipment, geological layers, or the remains of objects that reached the seafloor long before. New sediment then settles over the disturbed surface, separating what lies below from what arrives later. For geologists, this creates a difficult kind of history. The seafloor preserves evidence, yet it also continually rearranges and covers that evidence. A layer can be folded, fractured, buried, and covered again, leaving only fragments available to later researchers. The trench, therefore, behaves less like a fixed archive and more like a record that is constantly being revised by gravity, earthquakes, and flowing sediment. Every fresh deposit adds another page, while covering portions of the pages underneath. Over immense stretches of time, the distinction between original surface and later burial becomes increasingly difficult to trace, especially where steep walls feed material into deeper water. The geology remains active, and its record changes with every movement of sediment. The descent into the Milwaukee Deep changes the meaning of distance. At the bottom of the Puerto Rico Trench, nearly 8,400 meters below the surface, which is about 27,500 feet, the ocean becomes an environment governed by conditions far removed from ordinary experience. Pressure is the first transformation. Water above the trench floor presses downward with extraordinary force, reaching roughly 830 times the pressure found at sea level. The force is close to 12,000 pounds per square inch. A human body without protection could not withstand it. The pressure would compress air spaces throughout the body, while any exposed equipment would face forces far beyond those encountered at the surface. Temperature follows a different rhythm. At the trench floor, the water remains only a little above freezing, generally around 2 degrees Celsius or 36 degrees Fahrenheit. Sunlight contributes nothing to this warmth. Solar energy fades away within the upper ocean, while the deepest water receives heat only through the circulation of the ocean and the faint influence of Earth's internal energy moving through the crust. Light has another boundary altogether. By roughly 200 meters, which is about 656 feet, sunlight has dwindled beyond useful vision. Far below that depth, the Milwaukee Deep exists without natural illumination. The water column overhead separates the floor from the day and night cycle at the surface, leaving the deepest habitats in an environment where darkness is a permanent physical condition rather than a passing part of the day. Even the chemistry changes with depth. Seawater carries dissolved salts, gases, organic material, and particles that move through different layers at different rates. Oxygen concentrations vary as water masses travel through the Atlantic, and some intermediate regions contain oxygen minimum zones where respiration and circulation create unusually low concentrations. Near the deepest floor, sediments accumulate material carried downward from higher waters, while chemical reactions within those sediments alter the surrounding water. The pressure and chemistry also shape the organisms that can survive there. Many deep ocean animals possess flexible tissues and reduced air spaces, adaptations that allow their bodies to function where ordinary surface anatomy would fail. Microorganisms living within the sediment draw energy from chemical reactions involving minerals and organic compounds. Life remains present, but its energy economy is built around processes that scarcely resemble the familiar rhythm of sunlight-driven ecosystems. At these depths, there is also no simple boundary separating the geology from the biology. Water interacts with rock. Sediment consumes and releases dissolved compounds, and microorganisms transform chemicals within the seafloor. The trench floor becomes a meeting place between physical pressure, mineral chemistry, and living systems. Nearby, another source of chemical energy enters this deep environment. Methane moving upward through seafloor sediments can emerge at seep sites where specialized communities gather around a substance that would be associated with fuel at the surface. There, microorganisms use methane as an energy source, while larger animals depend on the chemical partnerships created around them. The deepest ocean, therefore, has its own kind of landscape, measured through pressure, temperature, chemistry, and biological adaptation. Nothing needs to resemble the surface for life to continue. The rules are different, yet they remain consistent with the same physics that governs every layer of the ocean. At the seafloor, methane can become more than a gas moving through sediment. It can become the foundation of an entire living community. Around seep sites, methane escapes through cracks and pores at a steady pace, feeding organisms that have built an energy system independent of sunlight. The process is called chemosynthesis. Specialized bacteria use chemical energy from methane or hydrogen sulfide to produce organic matter that can support other organisms. Their work replaces the role that sunlight plays in ordinary marine food webs. In that exchange, minerals and gases become nourishment, allowing a community to persist far beyond the reach of ordinary photosynthesis. White and orange bacterial mats spread across sediment near active seeps, forming living surfaces where chemical energy enters the food chain. Tube worms are among the most distinctive residents. Some reach nearly 2 meters, which is about 6.5 feet, and remain anchored in the sediment while their bodies extend into the surrounding water. They have no mouth and no digestive tract. Instead, an internal organ called the trophosome contains dense populations of bacteria. The bacteria receive oxygen and other substances through the worm's circulation, while the worm receives organic compounds produced by its microbial partners. Their association is so complete that the animal depends on its bacteria for nutrition. Nearby, mussels and clams gather into dense beds. Many carry bacteria within specialized tissues, allowing them to obtain energy from chemicals associated with the seep environment. From above, a concentrated bed can resemble a rough pavement spread across the sediment. The impression is almost architectural, although every surface is alive and responding to the chemistry moving through the water. Small predators occupy the same community. Crabs move among the shells and bacterial mats, feeding where opportunities appear. Fish with elongated bodies pass through the seep habitat, hunting smaller animals and scavenging material from the seafloor. Each organism occupies a place in a food web whose original energy comes from compounds rising through the sediment. The discovery of such ecosystems transformed marine biology. In 1977, scientists exploring hydrothermal vents in the Pacific encountered communities flourishing around chemical energy sources far below the reach of sunlight. The findings showed that ecosystems could be sustained by chemistry alone, expanding the known boundaries of life on Earth. Methane seeps differ from hot hydrothermal vents in temperature and chemical composition, yet they share the central principle of biological energy drawn from the Earth itself. Around the Blake Plateau, seep communities remain comparatively difficult to study. Deep water, rough terrain, and the limited reach of research vehicles restrict how much of the seafloor can be observed directly. Short expeditions can reveal clusters of organisms, but they capture only fragments of a much larger habitat. Some animals encountered during deep-sea surveys remain difficult to classify, especially when observations are brief or specimens are unavailable. A living community can therefore exist for years before science has enough evidence to give every species a place in its records. The significance of these seep habitats lies in their independence from the surface. Their food web begins with chemicals rising from sediment, passes through bacteria, and expands into animals that feed, hunt, and reproduce in a realm where sunlight has no role. The energy arrives from below, and life gathers around it. A layer of seafloor sediment can hold a history far older than any vessel that has crossed the Atlantic. Each grain settles into place alongside particles carried from distant waters, while fragments of living organisms become part of the accumulating record. Far below the communities gathered around seep sites, this archive reaches into the beginnings of the Atlantic itself. The methane found within these sediments has a biological ancestry. Microscopic organisms lived, died, and sank through the water column, joining the remains of larger creatures that eventually reached the ocean floor. Diatoms, tiny, drifting animals, fish, and whales all contributed organic carbon to the sediment. With repeated burial, pressure compressed these remains into layers that became increasingly isolated from oxygen. That lack of oxygen changes the chemistry of decomposition. Microorganisms working without oxygen break down organic material through anaerobic processes, producing methane among the resulting compounds. The gas can then move through pores and fractures in the sediment, following pathways toward shallower layers. Where pressure and temperature fall within the necessary range, methane combines with water to form a crystalline solid called methane hydrate. The sediment itself preserves more than the ingredients that produced this gas. Its layers record changes in the ocean above them. Variations in microscopic fossils can reveal shifts in temperature and biological productivity. Chemical signatures can preserve evidence of changing seawater conditions. Sediment grain sizes can indicate stronger currents, storms, or changes in the sources supplying material to the seafloor. Read together. These layers form a sequence of environmental snapshots extending far beyond written history. Even the absence of certain organisms can matter, because gaps in the record may mark changes in oxygen, circulation, productivity, or sediment supply across the basin. Ocean drilling has allowed scientists to recover cylindrical cores from these deposits. A core can contain successive layers arranged in chronological order, with younger material near the top and older material farther down. The deepest portions can reach back toward the Jurassic period, when the Atlantic was beginning to open as the supercontinent Pangaea separated. That transformation began roughly 180 million years ago, creating new oceanic crust and gradually establishing the basin that exists today. The oldest sediments associated with that early Atlantic are now buried under enormous accumulations of material. Their original surfaces have long since disappeared from view, sealed beneath layers deposited by countless generations of marine life. Pressure has altered their structure, while chemical reactions have transformed some of the organic matter within them. What remains is a compressed record of a changing ocean. Methane, therefore, carries two histories at once. One is chemical, describing how buried organic matter was transformed and how the resulting gas migrated through sediment. The other is biological, reaching backward through generations of organisms that lived above the same basin. The hydrate deposits preserve part of that inheritance in a form shaped by pressure, temperature, and time. At the Blake Plateau, the sediment column is more than material covering the crust. It is a layered memory of an ocean that has changed for millions of years, Every buried interval represents a former surface, a different community, and a different chemistry. The methane within those layers is one expression of that history, held in place where the conditions allow it to remain. The ocean beneath the triangle belongs to a planet that is still rearranging itself. Its boundaries may look permanent from an aircraft or a ship, yet the crust below is participating in motion measured across years, centuries, and immense spans of geological time. Far from the surface, the mid Atlantic ridge forms a great underwater mountain system running through the Atlantic basin. Along this ridge, material from the mantle rises toward the seafloor, cools, and becomes new oceanic crust. As fresh crust moves away from the ridge, the ocean floor spreads in opposite directions. The Americas gradually travel westward, while Europe and Africa move eastward, widening the basin between them. Across parts of the central North Atlantic, this spreading occurs at roughly 1 inch each year, a distance close to the width of a fingertip. 1 year leaves almost nothing visible. A million years produces movement measured in miles. Across roughly 180 million years, the accumulation becomes thousands of miles, transforming a narrow opening between fragments of Pangaea into the broad Atlantic Ocean known today. The motion also reaches into the geography associated with the Bermuda Triangle. The region is not a rigid shape, anchored permanently to the planet. The plates carrying its surrounding land masses continue to shift, changing distances between points on opposite sides of the ocean. Miami and the Canary Islands, for example, participate in the wider separation created by Atlantic spreading, although their exact change in distance depends on the directions and rates of the plates carrying them. Ocean crust preserves this movement like a slow conveyor. Rock formed near the mid-Atlantic ridge begins a long journey away from the ridge, becoming progressively older with increasing distance. Magnetic minerals locked into cooling basalt preserve changes in Earth's magnetic field, creating bands that mirror one another on opposite sides of the ridge. These patterns became important evidence for seafloor spreading, showing that new crust was continually being produced and carried outward. The floor of the Atlantic therefore contains different generations of crust arranged across enormous distances. Each generation carries traces of the conditions under which it formed, including the chemistry of seawater, the sediments that settled upon it, and the magnetic orientation preserved within volcanic rock. The seafloor becomes a map of motion, written in stone rather than ink, preserved across geological ages. Near the ridge, the seafloor is relatively young. Farther away, it carries a longer record of geological time. The crust beneath the Bermuda Triangle belongs to this moving system, traveling with the North American and Caribbean plates while interacting with faults, sediments, and the deeper structures around the basin. Nothing in this arrangement lasts forever. Ocean basins open, expand, and eventually begin to close as tectonic plates change direction over geological time. The Atlantic is expected to continue widening for a long interval, although the exact future depends on how the surrounding plate boundaries evolve. Supercontinent cycles have repeatedly reorganized Earth's oceans, closing older basins and creating new ones elsewhere. Seen across ordinary human time, the Atlantic appears almost perfectly still. Measured against the machinery of plate tectonics, it is a moving surface. The seafloor beneath the triangle is one moment within a planetary process that began long before modern geography existed and will continue long after today's coastlines have become part of Earth's geological record. At the center of the triangle, the sea takes on a geography made from motion. No shoreline marks the Sargasso Sea. Its boundaries are written by currents, each one carrying water along a different edge of a great circulation in the North Atlantic. To the west, The Gulf Stream sends warm water northward. Along the northern boundary, the North Atlantic Current continues that movement. Farther east, the Canary Current carries cooler water southward, while the North Atlantic Equatorial Current completes the circuit along the southern side. Together, these flows form a clockwise gyre, leaving the Sargasso Sea within its broad interior. Water can remain there for long periods, circulating through a region whose borders shift with the currents themselves. Summer brings surface temperatures close to 85 degrees Fahrenheit. Across that warm water float mats of sargassum, a golden brown seaweed that lives without anchoring to rock or sediment. The plants gather into drifting patches, sometimes stretching for miles, creating a floating habitat above the open Atlantic. Small fish weave among the fronds. Crabs cling to stems. Shrimp move through the tangled growth, feeding and sheltering within a world that travels wherever the surrounding water carries it. The seaweed itself becomes part of the landscape. As old fronds break apart, fragments and associated organisms become food for animals nearby, while some material sinks away from the surface. The floating mats, therefore, connect the sunlit layer with deeper parts of the ocean, carrying living matter through the water as the currents continue their slow circulation. Its branching surfaces provide places for tiny organisms to feed, reproduce, and avoid larger predators. Young fish can find cover among the strands, while other creatures graze upon the algae and the communities growing across it. A piece of sargassum can therefore function like a miniature reef, except that its foundation moves with the ocean. The circulation around this region also creates unusual surface conditions. Winds within the center of the gyre can be weak, allowing the water to appear almost undisturbed for stretches of time. Sailing vessels once depended heavily on wind, and entering this part of the Atlantic could leave a ship advancing at little more than the speed of its surrounding currents. Supplies became important when progress depended on weather that refused to arrive. Another traveler belongs to this sea in a more intimate way. The American eel begins its reproductive journey from rivers and streams across eastern North America, eventually reaching the Sargasso Sea. Adults arrive after traveling from freshwater habitats that may lie thousands of miles away. There, they reproduce, and their larvae begin a different passage, carried westward by ocean circulation toward the coast. Those larvae eventually reach estuaries and rivers, where they develop through several stages before entering freshwater habitats. Years later, mature eels undertake the return journey toward the same broad ocean region. Scientists have studied this remarkable migration for generations, examining ocean currents, magnetic sensing, chemical cues, and other possible guides. The full navigation system remains difficult to resolve. The Sargasso, therefore, connects distant environments through circulation and life. Warm water arrives from one direction. Currents continue around its perimeter. Floating algae support a mobile community, and an animal born in the open Atlantic begins a journey toward rivers thousands of miles away. Its geography is made of moving water, and its biological connections reach far beyond the surface visible from above. Above the sea, another pattern can emerge, one written into clouds rather than currents. Along the western edge of the Bermuda Triangle, near the Bahamas, satellite observations have revealed formations whose geometry appears unusually precise. Their straight boundaries give the atmosphere a shape that seems almost drawn across the sky. In 2016, meteorologists examining moderate resolution, imaging spectroradiometer, satellite imagery from 2002 identified these formations over the Bahamas. Several clouds displayed six-sided outlines, with broad edges extending across distances from about 32 kilometers, which is about 20 miles, to 89 kilometers, which is about 55 miles. Ordinary cloud fields usually develop softer, irregular boundaries as turbulent air mixes through them. These shapes suggested that a more organized process was acting near the lower part of the cloud. Dr. Steve Miller, a satellite meteorologist at Colorado State University, described straight cloud edges as unusual because clouds generally form with irregular distributions. The geometry became meaningful when researchers considered what might be happening below the cloud base. A microburst can send a concentrated column of descending air toward the surface. As that colder air reaches the ocean, it spreads outward, producing strong horizontal winds across the water. The process begins high enough to remain part of an ordinary storm system, yet its effects can become sharply concentrated near the sea. Air descending from a cloud can accelerate as it falls, carrying momentum downward before striking the surface and spreading outward. When several downdrafts develop within one cloud field, their outward flows can organize the surrounding cloud edges into angular patterns. The resulting shapes are therefore traces of motion, preserved for a brief time in the clouds above. Comparable formations have been observed over the North Sea near the United Kingdom. Measurements there have recorded surface winds reaching about 274 kilometers per hour, which is about 170 miles per hour. For comparison, the threshold for a Category 5 hurricane is about 253 kilometers per hour, which is about 157 miles per hour. Such winds can place enormous stress on the ocean surface, producing steep waves and rapidly changing conditions for vessels caught beneath an active downdraft. Dr. Randy Cerveny, a meteorologist at Arizona State University, has described these oceanic hexagonal patterns as air bombs, a phrase meant to convey the concentrated force of descending air. A microburst can form, strike the surface, spread outward, and dissipate within less than an hour. By the time observers search for evidence, the cloud system may have traveled far from the location where the strongest winds occurred. A formation covering a region with a radius of about 48 kilometers, which is about 30 miles, could influence a broad area of open water while remaining temporary from the perspective of a satellite record. The exact wind speed under every hexagonal cloud over the Bahamas remains uncertain because direct measurements during an active event are limited. What can be observed is the geometry itself, a fleeting signature of organized atmospheric motion. The ocean below continues to receive the force of these descending currents, while the clouds above record their passage in shapes that last only briefly. For a moment, the atmosphere becomes a map of the invisible air moving through it. For centuries, sailors carried home accounts of waves that seemed to belong to another scale. A sea could appear manageable, then a towering wall would rise without the gradual buildup expected from ordinary swells. Reports of 80, 90, or 100 feet became part of maritime folklore, while mathematical wave theory offered little room for such events. Without instruments to capture them, the stories remained difficult to verify. That changed on January 1st, 1995, when an oil platform in the North Sea named Draupner carried instruments capable of recording the movement of the water around it. At 3:20 in the afternoon, the equipment registered a wave about 26 meters high, which is about 85 feet. The surrounding sea was much lower, making the crest more than twice the significant wave height. A shape that had seemed almost impossible had entered a scientific record. A rogue wave is now understood as a wave exceeding twice the significant wave height of the surrounding sea state. If ordinary waves reach about 6 meters, that is nearly 20 feet, a rogue wave begins above 12 meters, which is about 39 feet. Some can rise far higher, heights approaching 30 meters, that is nearly 98 feet, have been observed, creating moving walls comparable to buildings while carrying enormous energy across the ocean. Satellite observations later showed that these events were not confined to one platform or one region. During a 3-week survey of the world's oceans, satellite radar detected dozens of unusually large waves. Their presence revealed a broader ocean process, where separate wave systems can interact, reinforce one another, and concentrate energy into an exceptional crest. The sea can therefore gather energy across several directions before releasing it through a single moving form. The Bermuda Triangle occupies a setting where several oceanic forces meet. The Gulf Stream carries water toward the northeast, while swell generated elsewhere can travel in opposing directions. Storm systems moving across the North Atlantic can add another family of waves, while tropical weather develops farther south. When these systems overlap, waves with different heights, periods, and directions can interfere constructively, allowing some crests to become much larger than the surrounding field. Oceanographer Dr. Simon Boxall of the University of Southampton has described the region as a meeting place for distinct storm systems, including North Atlantic winter storms, Caribbean tropical systems, and swells associated with the Gulf Stream. Their interaction creates conditions where wave energy can become concentrated. The process requires no unusual force from outside the ocean. It emerges from ordinary movements combining in an unusual arrangement. For a vessel, the important detail is duration. A large rogue wave may pass in less than a minute, leaving little time for a response once its face rises ahead. A wave approaching 80 feet, or about 24 meters, could strike with tremendous force, while a crest near 100 feet, or about 30 meters, could overwhelm a vessel designed around more predictable seas. Before modern satellite observations, such a wave might leave only scattered evidence afterward. The old reports, therefore, occupy a different place in the history of the sea. They were observations made without instruments capable of proving them. Today, measurements from platforms, ships, and satellites show that extreme waves belong to the natural behavior of the ocean, formed when ordinary systems briefly gather their energy into an extraordinary shape. Every force gathered across this stretch of ocean has a counterpart elsewhere. The Gulf Stream belongs to a worldwide system of currents. Methane hydrates line continental margins on many sides of the planet. Deep trenches mark zones where one tectonic plate descends beneath another, while gyres turn through every major ocean basin. Chemosynthetic communities live around cold seeps and hydrothermal vents from the Gulf of Mexico to the Norwegian Sea. Rogue waves have been recorded in the Southern Ocean, the North Sea, and the South Atlantic. What gives this region its particular character is the overlap. A broad area of roughly 500,000 square miles brings together ocean circulation, unstable weather, deep geology, unusual chemistry, and specialized biology. Each system follows its own rules, yet their boundaries touch. A current can alter the movement of heat and moisture above the sea. Waves can meet from different directions. Sediment can preserve organic material that later becomes methane. The floor of the ocean can descend into one of the deepest places on Earth. The Gulf Stream adds another layer to this arrangement. Its warm water crosses a cooler environment, helping shape atmospheric conditions and moving rapidly through the region. Storms passing over the current can draw energy from the temperature difference between ocean and air. Once a vessel or aircraft disappears, that same circulation can carry fragments far from the original location, complicating reconstruction of what happened. Far below, methane deposits represent another piece of the puzzle. Gas formed within buried sediment can become trapped as hydrate under suitable pressure and temperature conditions. Disturbance of the seafloor can alter that balance, although the precise connection between methane release and historical disappearances remains unproven. The deep trench adds a separate obstacle. Material reaching its floor enters an environment where recovery becomes extraordinarily difficult, leaving little opportunity for ordinary searches to reconstruct an entire event. Above the water, the Sargasso Sea gathers around the center of a rotating ocean circulation system, while weather can arrive from several directions. Rogue waves emerge when wave trains interact and concentrate their energy. Powerful downdrafts can also descend from storm clouds, producing abrupt changes across the sea surface. None of these processes requires an unusual law of nature. Each follows familiar physical principles under particular conditions. The geological foundation adds another dimension. The western North Atlantic contains old oceanic crust, continental margins, deep faults, and structures shaped by the continuing movement of Earth's plates. Gravity variations reflect differences in the materials below the seafloor, giving scientists another way to trace the architecture of the planet beneath the water. Seen together, these features form a setting where several difficult conditions can occur within the same broad region. The ocean does not need to behave differently here. It only needs several ordinary systems to overlap at the same time. That distinction changes the meaning of the triangle. Its reputation grew around stories of disappearance, but the physical setting is more interesting than any single legend. Currents, weather, waves, sediment, tectonic movement, and living communities have occupied this part of the Atlantic for immense spans of time. The remarkable feature is their convergence, a meeting of natural processes that makes this piece of ocean unusually complex and gives every layer of it a different way to shape what happens above. A name can change the shape of a story long after the place itself has remained exactly where it was. In February 1964, writer Vincent Gaddis introduced the phrase Bermuda Triangle in Argosy magazine, drawing a triangle across a map and gathering a collection of disappearances beneath its new title. The reports were presented together, yet the underlying records were not examined with the same care. Traffic volume, weather conditions, confirmed recoveries, and the actual locations of incidents received little attention. A decade later, Charles Berlitz carried the story much farther. His 1974 book became a publishing phenomenon, selling nearly 20 million copies in 30 languages. Within its pages, ordinary uncertainty was joined by Atlantis, disturbances in time, and visitors from elsewhere in the universe. The triangle became more than a geographical description. It became a narrative space where unanswered events could be placed beside ideas that belonged to entirely different realms. Then a reference librarian named Larry Couchet began tracing those claims back toward their sources. For 2 years, he compared the published accounts with contemporary records, including maritime insurance files, reports from the United States Coast Guard, ship logs preserved in national archives, and weather records from the dates in question. The pattern changed as each account was returned to its original documentation. Some vessels described as missing had later been found. Some incidents said to have occurred under calm skies coincided with documented storms. Several events had taken place hundreds of miles outside the supposed boundaries. The correction was less dramatic than the legend, yet more revealing. A disappearance could become more mysterious when the surrounding facts were removed. A storm could vanish from the story when only the loss of a vessel remained. A recovered ship could continue appearing in later retellings if an old list was copied without checking what happened afterward. With every omission, the distance between an event and its description grew. The maritime world offered another measure. Lloyd's of London, one of the oldest insurance markets serving ocean commerce, did not impose special insurance rates for vessels crossing the Bermuda Triangle. Modern assessments of maritime risk instead follow measurable factors such as weather, traffic density, navigation, vessel condition, and regional hazards. A global shipping study published by the World Wildlife Fund in 2013 identified other corridors with higher incident rates, while the Bermuda Triangle did not appear among the 10 most dangerous. The legend, therefore, became a kind of historical artifact, preserved through repetition. Its strength came from the space between what happened and what could once be observed, recorded, and verified. Before satellites, global positioning systems, continuous weather monitoring, and modern oceanographic instruments, much of the sea existed beyond direct human observation. A vessel could disappear into distance, a storm could pass, and currents could scatter evidence across hundreds of miles before anyone arrived. Better instruments gradually narrowed that gap. Weather systems could be tracked across the ocean. Ships could transmit their positions. Search teams could reconstruct currents, winds, and sea conditions with greater precision. The stories became easier to test, and many lost their supernatural shape when placed beside the records that had always been there. The ocean remained the same body of water, following the same currents and physical laws. What changed was the amount of it that humans could see. The ocean has become easier to read from above, below, and across its moving surface. A vessel crossing the Bermuda Triangle today carries instruments that turn position into a continuous stream of information. The global positioning system became fully operational for civilian use in 1995, replacing the uncertain calculations of earlier navigation with coordinates that can place a vessel within roughly 3 meters, which is about 10 feet. Position is no longer something reconstructed from a compass, clock, and estimated speed after the journey. It is measured as the journey unfolds. Emergency position, indicating radio beacons, add another layer of protection. On commercial vessels, these devices can activate when a ship enters the water, transmitting an emergency signal associated with its position. Satellites receive the transmission and pass the information towards search and rescue authorities, allowing responders to begin with a location instead of an empty stretch of ocean. The difference is profound when currents are moving and weather is changing. A search that once depended on estimates can begin from a recorded point. Above the sea, weather satellites provide an equally important transformation. Clouds developing over the western North Atlantic can be followed as organized systems, with their movement, structure, and growth observed from orbit. Squalls crossing the Gulf Stream can be monitored as they form and evolve. The strange geometric cloud patterns associated with powerful downdrafts can also be identified from space, giving meteorologists a way to connect what appears above the ocean with the conditions developing at its surface. The vessels themselves have changed as well. Modern hull design relies on calculations of stability, buoyancy, structural strength, and behavior in severe seas. Computer models can test how a ship responds when waves arrive from different directions or when an unusually large crest passes through a surrounding sea state. Engineering standards now incorporate lessons gathered from decades of observations, measurements, accidents, and full-scale testing. A vessel is therefore designed with a far richer understanding of the ocean than one available to builders generations ago. Far below, mapping technology has transformed the seafloor from an imagined landscape into something measurable. During the Five Deeps expedition in 2018, sonar systems mapped the Milwaukee Deep with a level of detail that earlier explorers could never have obtained. Features of only a few meters, which are about a few feet across, can be distinguished in modern surveys, allowing ridges, slopes, sediment structures, and other formations to be examined systematically. This does not make the ocean predictable. Storms still form, currents still move, and waves still obey forces that can become difficult for any vessel to withstand. The difference lies in the information surrounding those events. A ship can transmit its position, a storm can be tracked, a changing sea state can be measured. A missing signal can be located against a much clearer geographic picture, while drifting debris can be modeled against currents and wind. Even partial evidence can now retain its place within a larger sequence of events. Digital records can preserve observations across hours and days, allowing investigators to compare position, weather, currents, and vessel behavior after an incident. The era of unexplained disappearance belonged partly to an age when enormous portions of the ocean were beyond continuous observation. Modern instruments have narrowed that darkness. The water remains dynamic, the weather remains changeable, and the deep floor remains difficult to reach. What has changed is the human view, now extended across distances and depths that earlier generations could only imagine. The map of the ocean floor is still a work in progress. Even after decades of sonar surveys, satellite measurements, research cruises, and deep diving expeditions, enormous portions of the seabed remain represented by broad outlines rather than detailed terrain. In 2026, the Seabed 2030 project reported that 28.7% of the world's ocean floor had been mapped to modern standards. More than 70% remained outside that level of coverage. Those numbers become more striking when depth is considered. The mapping standards used by the project allow different resolutions at different depths because surveying becomes harder as water gets deeper. In the deepest zones, the target grid can reach 800 meters, which is about 2,620 feet across, so a feature can exist between measured points without appearing clearly in the final map. A seafloor canyon, sediment ridge, fracture, or landslide scar may therefore be present without its finer shape being known. The Bermuda Triangle sits within this larger uncertainty. Its surface waters have been crossed by countless vessels, studied by satellites, and photographed from aircraft, yet the deeper terrain remains far less familiar than the landscape above it. Parts of the Puerto Rico Trench and the surrounding continental margins have been surveyed with modern multi-beam sonar, while other areas still depend on older measurements collected from widely separated tracks. The Blake Plateau has also received focused mapping, but detailed coverage remains uneven across such a large region. The difference between a broad map and a detailed one matters. A coarse survey can reveal the general depth and shape of a basin, while high resolution can expose channels, ridges, scarps, sediment waves, and other structures that reveal how the seafloor was formed. These smaller features can influence currents near the bottom, guide sediment movement, and preserve evidence of landslides or other geological events. Each new survey can therefore change the story told by the ocean floor. The Five Deeps expedition offered a glimpse of what happens when explorers finally reach places that have received little direct attention. In December 2018, its submersible reached the deepest point of the Atlantic in the Puerto Rico Trench, after the expedition team used multi-beam sonar to identify and verify the deepest area. The survey work refined the position and depth of the Atlantic's deepest point, demonstrating how much precision can emerge from direct observation. Life below the surface remains similarly incomplete in its catalog. Cold seep communities around the Blake Plateau have been explored during scientific expeditions, including mapping and biological observations, yet the deep ocean is revisited far less often than coastal environments. A species encountered during one survey may remain difficult to study if the same seep is not examined again under comparable conditions. The strange part is that none of this requires anything to be concealed. A ridge does not need to hide. A seep does not need to disappear. A trench does not need to keep its history from us. The limitation is distance, depth, cost, time, and the immense area of ocean that must be measured one survey line at a time. The Bermuda Triangle may be famous on maps, yet much of its deeper world remains known only in fragments. A current crossing the Atlantic can carry the memory of distant sunlight. Heat gathered near the tropics travels northward through the Gulf Stream, while the water beneath the Bermuda Triangle participates in a circulation that reaches far beyond any map drawn around this region. The ocean here is part of a planetary exchange, moving energy, dissolved substances, sediments, and living organisms through pathways that connect separate environments. The Gulf Stream carries enormous amounts of heat toward higher latitudes, helping shape weather and climate across the Atlantic basin. Warm water gives heat to the atmosphere as it moves, while colder, denser water elsewhere sinks and continues the circulation at depth. This global overturning movement links surface conditions with the deep ocean, allowing changes in one part of the system to influence distant waters. The triangle therefore rests inside a moving climate mechanism whose boundaries extend far beyond its familiar outline. Carbon stored within methane hydrates belongs to another planetary cycle. Methane formed from buried organic material can become trapped within ice-like structures under particular combinations of pressure and temperature. Where these deposits meet the seafloor, some methane reaches the surrounding water and supports specialized microbial communities. The carbon then moves into food webs, sediments, and seawater, taking different forms as it passes through the ecosystem. A substance locked away for long periods can become part of active biology when geological conditions allow it to escape. Far below, the Puerto Rico Trench belongs to Earth's larger process of crustal recycling. Tectonic plates move across the planet, collide, bend, fracture, and descend into the mantle. The same broad machinery that shapes trenches also generates earthquakes and helps build volcanic regions elsewhere. Sediment accumulating above these structures records the movement of water, rock, and organic material, while pressure and chemistry alter what becomes preserved. The Sargasso Sea adds another layer to this circulation. Its position within the North Atlantic Gyre allows floating organisms to remain within a broad rotating system for extended periods. Sargassum provides shelter and food for small animals, while its growth and decay move nutrients and carbon through surface waters. The gyre is therefore more than a pattern of currents. It creates a particular biological setting through the combined influence of movement, sunlight, nutrients, and temperature. At the seafloor, chemosynthetic communities transform another kind of energy into living matter. Microorganisms use chemical compounds rising from geological sources, including methane at some seep sites, and convert that chemical energy into organic material. Small animals feed on these microorganisms, larger organisms feed on them in turn, and the resulting web connects geology with biology. Each process remains distinct, yet none operates alone. Circulation moves heat and material. Tectonics shapes the ground where sediments accumulate. Sediments influence the conditions surrounding methane deposits. Methane supports microbial life, while organisms alter local chemistry. Water then carries some of those substances onward. The connections are gradual and often difficult to see, but they form a continuous exchange across ocean, atmosphere, rock, and life. Seen this way, the Bermuda Triangle becomes less a boundary than a meeting place within Earth's larger machinery. Its waters participate in processes that cross oceans and endure for millions of years. What appears to be one small region on a map is part of a planetary system, always moving, exchanging, transforming, and becoming something slightly different with every passing moment. A ship can cross the same patch of Atlantic on 2 different days and encounter two entirely different arrangements of wind, waves, currents, and weather. The water beneath both journeys belongs to systems that began long before the first vessel entered these seas. Human presence arrives for a moment, leaves a trace, and disappears, while the ocean continues along rhythms measured in centuries, millions of years, and deeper spans of geological time. The Gulf Stream, in its present broad configuration, has existed for roughly 2 million years, although Atlantic circulation itself reaches much farther into the past. Its waters have moved through the western Atlantic during periods when human ancestors were only beginning to change. The current flowed before ships carried names across these waters, before charts gave the region boundaries, and before anyone imagined a triangle upon a map. Its movement depends on temperature, salinity, wind, and the rotation of Earth, all operating independently of human attention. Far below the surface, methane hydrates preserve another record of time. Organic material produced by marine life settled into sediments and became buried beneath later layers. Under suitable pressure and temperature, methane became enclosed within ice-like structures. Some of these deposits began forming tens of millions of years ago when the oceans supported ecosystems very different from those of today. Their carbon belongs to a history that reaches through changing climates, shifting coastlines, and generations of organisms that never encountered a human being. The Puerto Rico Trench carries an even older memory. The tectonic boundaries around the Caribbean have evolved through immense changes in the arrangement of Earth's crust. Parts of the region have been shaped by plate movements extending back more than 100 million years. Rock has fractured, folded, descended, and risen through processes that continue regardless of whether a vessel passes overhead. The deep structure beneath the water therefore belongs to a planetary history that began long before the Atlantic acquired its modern outline. Even the gravity variations measured around the sea floor are expressions of this deeper machinery. Differences in rock density and the arrangement of crust beneath the ocean influence the gravitational field from place to place. These patterns develop through geological processes unfolding across enormous spans of time. A human lifetime is brief beside them, a small interval within a system that continues without pause. For several centuries, people have crossed these waters regularly enough to build routes, legends, records, and expectations around them. The ocean has never shared those categories. It responds to pressure, heat, density, gravity, wind, and moving water. A vessel enters those conditions with a limited structure and limited knowledge, then passes beyond them. The surrounding systems continue whether anyone is watching. The loss of a ship can therefore become an intersection between two very different scales. Human construction may endure for decades, a storm may last hours, a current may persist for millions of years, A trench may evolve across geological ages. When those scales meet, the shorter lived object is the part that changes first. The Cyclops disappeared in 1918, yet the forces acting upon its passage existed long before that ship was built and remain active today. Nothing in the ocean had been waiting for it. The same currents, pressure systems, waves, and geological structures continue their movement when no vessel crosses above them, carrying Earth's story forward without awareness of the people passing through. There is a strange intimacy to the ocean's surface at night. From a vessel, the water occupies the narrow field that human senses can reach, a moving skin shaped by wind, current, and light. Everything below that boundary belongs to another physical world. Water may be carrying heat, sediment, dissolved chemicals, and living organisms in directions that cannot be perceived from above. Within the Bermuda Triangle, the Gulf Stream moves northeast at about 5.6 miles per hour, transporting warm tropical water toward the North Atlantic. Its flow is part of a much larger circulation, and its movement can disperse floating material across the sea. What appears to be one uninterrupted surface therefore conceals a river within the ocean, broad enough to influence weather and climate far beyond the region. Surface conditions can change within minutes, while deeper currents follow patterns established by density and geography. A vessel experiences only the portion that reaches its hull, instruments, and senses. Much of the surrounding machinery continues outside that boundary, carrying materials through layers of water that rarely meet the human eye. On the Blake Plateau, sediments contain methane hydrates at depths of roughly 1,000 to 4,000 feet. These deposits form when methane becomes enclosed within ice-like structures under suitable pressure and temperature. Their carbon has accumulated through the burial and transformation of organic material over geological ages. Around some seep areas, microorganisms use chemical energy associated with methane and other compounds, supporting communities that function without sunlight reaching their habitat. Farther down, the continental slope gives way to the deep Atlantic, where the seafloor lies around 15,000 feet below the surface in parts of the triangle. At those depths, pressure becomes immense, temperatures remain low, and sunlight has long since disappeared. Yet the seabed remains active. Sediment settles, currents move particles, and organisms continue exchanging matter with their surroundings. Southward, the Puerto Rico Trench descends to about 27,493 feet at its deepest point. The walls record continuing tectonic movement, while pressure on the floor reaches roughly 12,000 pounds per square inch. Gravity measurements across the region also reveal unusual variations linked to the distribution of mass within Earth's crust. These signals are pieces of a geological structure that extends far beyond anything visible from the surface. To the east, the Mid-Atlantic Ridge continues its patient work. New oceanic crust forms where material rises from Earth's mantle, cools, and becomes part of the seafloor. The spreading rate in this region is close to 1 inch each year. A distance almost too small to notice during a human lifetime becomes substantial when repeated across millions of years, gradually widening the Atlantic basin. All these processes occupy the same planet at the same moment. A current carries heat overhead, sediments hold carbon below. Microorganisms transform chemicals near the seabed. Tectonic forces reshape rock farther south, while new crust emerges along the ridge. None of these layers needs to announce itself at the surface. From above, the Bermuda Triangle can resemble countless other stretches of open Atlantic. Under that surface, however, water, rock, chemistry, and life are engaged in continuous exchange. The visible ocean is only the uppermost page of a larger physical story, with deeper chapters unfolding beyond sight. There is no separate world beneath the Bermuda Triangle, waiting for a name. The deeper you travel through its waters, the more clearly the region becomes part of something older and larger than any human story. The features gathered here belong to Earth's ordinary machinery, operating at scales that make a human lifetime feel brief. Warm Atlantic water moves through the region as part of the Gulf Stream, carrying heat across the ocean and influencing weather far beyond the western Atlantic. Sediments on the Blake Plateau hold methane hydrates, compounds formed where methane becomes enclosed within ice like structures under pressure. Their carbon entered the seafloor through the remains of organisms that lived across immense stretches of geological time. Around some seep sites, microorganisms draw energy from chemicals rising through the sediment, supporting communities that function without sunlight. Farther south, the Puerto Rico Trench marks a boundary between enormous sections of Earth's crust. The descending plate carries oceanic material into the planet's interior, while pressure accumulates through continuing tectonic movement. Earthquakes release some of that stored energy, and the surrounding geological system has helped shape the Caribbean region for millions of years. The trench is therefore more than a deep depression. It is part of a planetary process that continually rearranges the surface. Gravity adds another layer to the picture. Measurements around the trench reveal variations in the gravitational field caused by differences in the distribution of mass within Earth. Such anomalies can help scientists infer structures that cannot be seen directly. Some aspects of the strongest anomaly remain unresolved, leaving an open scientific problem within a region already filled with measurable processes. Life occupies its own part of this arrangement. Chemosynthetic organisms can build ecosystems around chemical energy where sunlight never reaches. Bacteria process compounds such as methane and hydrogen sulfide, while larger animals depend on the resulting food web. Tube worms, mussels, and other organisms can gather around seep environments, turning geological activity into biological opportunity. Some deep-sea species remain poorly studied, and many communities have been visited only briefly. Above these layers, the ocean continues to move. The Gulf Stream can transport floating material and disperse traces over broad areas, while winds, waves, and currents alter the surface from hour to hour. A vessel passing through sees only a fraction of this motion. Its instruments may record position, weather, pressure, and wave conditions, yet enormous processes continue outside the range of ordinary perception. The old stories placed the mystery in the water as though something unusual had been concealed there. A different picture emerges from geology, chemistry, biology, and oceanography. Nothing needs to be added to make this region extraordinary. The planet already supplies enough complexity. What lies beneath is rock under pressure, water carrying heat, sediments storing carbon, chemicals feeding life, and gravity responding to hidden variations in mass. Each process follows physical laws that extend far beyond this one part of the Atlantic. Their convergence gives the region its character. The Bermuda Triangle therefore becomes less like a boundary on a map and more like a small window into Earth's larger system. The surface may carry a vessel for a few hours, while thousands of meters below, the planet continues its much older work. Human legends occupy only a moment above it. The water remains open, connected, governed by time. 62 years is enough time for a myth to become familiar, but almost nothing when measured against the life of an ocean. The Bermuda Triangle entered popular culture in 1964, gathered momentum through the 1970s, faced growing scrutiny during the following decade, and continued appearing in books and documentaries into the 2020s. Human memory gives this story a long shadow. Geological time gives it barely a footprint. The ocean beneath this region belongs to a different calendar. The Atlantic Ocean, in its present form, began opening roughly 180 million years ago, as continents separated and new crust formed along spreading centers. The tectonic forces shaping the Caribbean and Western Atlantic reach farther back still. At the Puerto Rico Trench, immense plates continue their slow movements, while gravity responds to differences in the distribution of rock deep within Earth. The anomaly measured there is part of a geological story whose earliest chapters existed before the Atlantic took its present shape. Even the carbon preserved in methane hydrates carries a history far older than human civilization. Organic matter settled through ancient seas, was buried by sediment, altered through chemical processes, and eventually became part of a cycle that continues today. Each deposit holds material inherited from ecosystems that existed long before anything resembling modern humanity appeared. The molecules have passed through countless transformations, while ships, maps, and legends occupy only a narrow interval near the surface of time. Sediment provides another kind of memory. Layer after layer accumulates on the seafloor, preserving fragments of biological activity, chemical change, erosion, and climate. A major extinction can leave a recognizable boundary marked by unusual chemistry and a sudden shift in the fossils contained within the sediment. Changes associated with colder periods can be traced through oxygen isotopes preserved in the shells of tiny marine organisms called foraminifera. Their proportions vary with global ice volume and temperature, allowing scientists to reconstruct conditions that existed long before written records. Storms may leave their own signatures. Powerful waves can disturb the upper sediment, mixing particles and creating structures that differ from the layers formed during ordinary deposition. A hurricane from 1918 would occupy only a thin disturbance within an archive that extends through thousands of years. If that disturbance remains identifiable at all, it exists as a physical trace rather than a narrative. The distinction matters because the ocean keeps a different kind of history from ours. Human records preserve names, dates, testimony, photographs, insurance documents, and stories passed between generations. The seafloor preserves particles, minerals, shells, organic compounds, and chemical ratios. One record follows the movements of people, the other follows the movements of Earth itself. From that perspective, the famous disappearances become brief events within a much longer sequence. The Gulf Stream continues carrying heat across the Atlantic. Sediment continues settling. Plates continue moving. Chemical reactions continue around deep seafloor communities. The planet does not arrange these processes around human chronology. A name can last for generations. A sediment layer can remain for millions of years. Between those two measures lies the scale at which the ocean becomes understandable, and the Bermuda Triangle becomes what it has always been, a small region of water inside a much older Earth. Far beyond any human calendar, there is a strange continuity in the surface of the Bermuda Triangle. It has the same basic appearance it had when Christopher Columbus crossed the Atlantic in 1492, with sunlight scattered across moving water and wind shaping the waves. Centuries later, on December 5th, 1945, the same ocean received 5 torpedo bombers that departed from Fort Lauderdale and never returned. In March 1918, the cargo ship Cyclops entered the western Atlantic, carrying 306 people and a load far beyond its rated capacity. The water gave each event the same setting it gives every passing vessel, an open surface stretching toward the horizon. From above, little of the deeper structure reveals itself. Several hundred meters below the surface, that is nearly 1,000 feet, the water can still belong to the immense circulation of the Atlantic. Farther down, sediment stores methane hydrates formed through processes that began millions of years ago. These deposits hold carbon within mineral and biological cycles that extend across geological ages. The continental slope descends toward deeper plains, while the Puerto Rico Trench reaches extraordinary depths farther south. Its fractured boundaries reflect the movement of tectonic plates, and its floor carries gravitational variations produced by differences in mass within Earth. Life occupies another layer of this same system. Around methane seeps, microorganisms obtain energy through chemical reactions that require no sunlight. Their activity supports larger organisms, creating communities adapted to conditions that would be impossible for most surface ecosystems. The existence of such life reminds us that darkness does not mean inactivity. Far below a passing ship, chemistry continues its work through sediment, rock, and water. The ocean floor also changes, although the movement is almost impossible to notice within a human lifetime. Along the mid-Atlantic ridge, molten material rises and cools into new crust. The Atlantic gradually widens as this process continues, at rates measured in inches each year. Geological motion on this scale has no need for an audience. It continues whether a vessel crosses overhead or whether the surface remains empty for 1,000 years. Above all these layers, currents carry heat and material across the Atlantic. The Gulf Stream transports an immense volume of warm water, linking tropical regions with the waters farther north. Wind, pressure, waves, and circulation reshape its surface from one hour to the next. A ship encounters these forces directly, while the deeper processes remain outside ordinary human perception. That continuity changes the meaning of the old stories. The vessels and aircraft were temporary structures moving through a system that had existed long before they arrived. The ocean did not become different for them. Human technology, navigation, engineering, and understanding were simply limited compared with the scale of the environment. Today, the same water continues moving across the same basin. The trench remains part of an active geological boundary. Methane remains stored in sediment. Chemosynthetic communities continue processing chemical energy. New crust continues forming far below the waves. None of these processes depends on the legends attached to the region. The surface still reflects the sky. Wind still draws patterns across it. A vessel can cross the same water beneath which Earth has been working for millions of years, carrying its processes forward without pause. The water is the same. Our understanding has changed.